तो हम पढ़ने वाले हैं वाइब्रेशनल स्पेक्ट्रोस्कोपी which is also known as infrared spectroscopy. Till now we have studied rotational. Now we'll go for vibrational spectroscopy. And vibrational spectroscopy lies in infrared region of the spectrum. Now, as compared to vibration, rotation is easy, vibration is hard. Means prepare the molecules will prepare rotation with lower energies as compared to the vibration. If you are increasing the energy, then first rotation will take place, and if you continue to increase the energy, vibration will also take place. Rotation and then vibration. Now, suppose we are having a diatomic molecule, vibrating diatomic molecule. So according to Hooke's law, what will happen? F equal to minus kx, and here kx is r minus r naught. F is, we know, restoring force, k is force constant, and the r is intermolecular distance between the molecules, atoms of the molecule, and r equivalent is the bond length, which is the stable equilibrium condition. So when you draw the graph between u and r, we have graph like this. Okay, so this is the r equivalent, means at this point if you go this side, then what will happen? You increase, means F will negative, so force will be this. If you go this side, means you will be negative, means negative negative positive, force will be positive, means again molecule will try to get back in its original position. So thus it is called as stable equilibrium. Now what will the energy for vibrational spectroscopy, vibrating molecules, equal to half k r minus r equivalent square. This is the important. We have to calculate the oscillatory frequency. We know that omega 2 pi by k, 2 pi n dot k by a m. We know this. So 2 pi omega, which is equal to f, 2 pi omega equal to not k upon mu, and omega oscillatory frequency 1 upon 2 pi c n dot k upon mu, which is in centimeter inverse. This is in hertz, and if you divide it by c, it will be in centimeter inverse. So remember this. Omega oscillator equal to 1 upon 2 pi c n dot k upon mu centimeter inverse. Now when we solve Schrodinger equation for these vibrational energy levels, what we are getting? The energy levels mu, E mu, energy of mu vibrational quantum number will be similarly n plus 1 by 2 h cross omega. Here mu plus 1 by 2 h omega. Okay, h omega for oscillatory, where omega is omega oscillations, frequency of omega oscillations, and here E mu equal to mu plus 1 by 2 omega in centimeter inverse. So it is in joule and it is in centimeter inverse. Remember this, E mu equal to mu plus 1 by 2 omega oscillation centimeter inverse. Now we will discuss about lowest possible vibrational energy. So for ground state, mu equal to 0, which is also known as 0 point energy. From here you calculate half h omega oscillatory, which is joule, and if you remove this h, then it will be held in terms of centimeter inverse. So 0 point energy will be equal to half omega opposite oscillation. Sorry. Now what will be the selection rules for vibrational transition? Delta mu equal to plus minus 1, means the change in vibrational quantum number should be plus or minus 1. Emission and absorption respectively. Vibrational energy change will only give rise to an observable spectrum if the vibrations can interact with the radiation. Okay, we know this. If the vibration involves the change, remember this, the change in dipole moment of molecule. So vibrational transition only possible when there is change in dipole moment. Okay, not necessarily if a molecule is having dipole, then it will show vibrational energy. We should have the change in dipole moment to have vibrational transition. Like this, I have explained it here. Like H2, N2 and O2 are inactive in rotation. Why it's inactive in rotation? Because they are not having permanent dipole moment. So it will be in rotational inactive. But in vibration, permanent dipole moment is 0. However, there is only change in dipole moment. Then they can show the vibrational transitions. So this is condition for only rotational, and for vibrational we should focus on the change in dipole moment. Now thus the vibrational, just read this line once, you will get it. Thus vibrational spectra will be observable only in heteronuclear diatomic molecules. Since homonuclear diatomic molecules have no permanent dipole moment as well as no change in dipole moment during vibration, means the vibrational spectra is observable only in heteronuclear diatomic molecules. Why not in homonuclear? Because homonuclear diatomic molecules have no dipole moment, है ना, zero होता है total. The dipole moment for homonuclear atoms is 0, so it will not show the vibrational transitions because it's not having permanent dipole moment as well as there is no change in dipole moment during vibration. Now for emission क्या होगा, देखो emission क्या होगा, हायर टू लोअर मीन्स म्यू माइनस म्यू प्लस वन ऐसा होगा. बट एब्जॉर्प्शन में क्या होता है, फ्रॉम बॉटम टू टॉप मीन्स क्या होगा, फाइनल माइनस इनिशियल माइनस फाइनल. सो ऑब्जर्वेशन वी कॉल इट इनिशियल माइनस फाइनल, एंड फॉर इनिशियल वी विल कॉल फाइनल माइनस इनिशियल. रिमेंबर दिस ना, or else you will be get confused that how we are calculating delta mu. Okay, so for emission it is final minus emission, final minus initial, and for observation we are having initial minus final. So this is for emission, this is for emission. So delta E equal to same formula, mu plus 1 by 2 omega of C3 for mu, and just put mu plus 1 for here, and you calculate delta E. Energy difference between is simply the frequency of oscillations. So for 0.5 omega oscillation 3 by 2 for 1, 2 and 3. So you can see here this condition, and the gap between two successive energy levels is omega, same as SHO. Now we will take enharmonic oscillator. This was for SHO. Now let's take a condition that the oscillator is enharmonic, means the real molecules don't exactly obey the law of SHM. The real bonds, although elastic but not too homogeneous as to obey Hooke's law. If the bond between the atoms is straight, for instance, there comes a point where it will break because elasticity will break at some point. Now molecules associates into atoms. The purely empirical expression सामूहिक, इसको बोलते हैं आनुभाविक, है ना, empirical, for enharmonic oscillator was given by PM Morse. Okay, so by in vibrational spectroscopy, when we are increasing the energy, what will happen, the molecules will try to dissociate because the bond is show elastic nature. So after a certain point in vibration, molecule will associate into atom, and this was given by PM Morse. So the Morse function is here, which is represented by a new coefficient D, which is dissociation energy. Okay, I try to speak fast, that's why what will happen, sometimes words got stuck in my lips. Okay, so just focus, you will listen it. A equal to D equivalent 1 minus exponential of A R E Q minus R square. Now we use by Schrodinger equation. What will happen in Schrodinger equation, mu plus 1 by 2 omega E minus mu plus 1 by 2 square omega E x E, which is in centimeter inverse, and chi is enharmonicity constant, and chi is 0.01, and omega is oscillatory frequency expressed in wave number. Now for enharmonic, mu equal to omega E bar 1 minus x c mu plus 1 by 2 mu plus 1 by 2. Now for harmonic oscillator, what will happen, mu equal to omega s c mu plus 1 by 2. So for enharmonicity we have introduced a new coefficient x c. Okay, so simply the harmonic and then correction term. same, but coefficient x, sorry. So this was the for expression for enharmonic, this was expression for harmonic. So just try to do the most function. This is r and this is t, which is dissociation energy. So mu 0, mu 1, mu 2, and then it will be continue. So when frequency increases, energy levels are getting closer. Okay, means this is enharmonicity. But for harmonic frequency, gap remains the same. In harmonic oscillator we were having, with increase the frequency, the gap was omega between two successive energy levels. But here energy, when we are getting the mu, energy levels are getting closer, like this, in the diagram like this. It is not perfect diagram, okay, just a schematic diagram. So what will happen? Omega oscillation for enharmonic, omega e 1 minus chi e plus 1 by 2. Thus in harmonic behaves like harmonic, but here as omega decreases steadily with mu increases. So only one difference is there, that in harmonic omega was constant, but here omega is decreasing with increasing in mu. Now suppose mu equal to 0, then completely what will happen? Omega e by 2 1 minus xc, and omega oscillator will be omega minus xc by 2. Now for enharmonicity, plus minus 1 plus minus 2, it will goes on, and for harmonic only plus minus 1 was there. Okay. Now we'll go for relative population for n equal to 1 to n equal to 0 to 1. Same Maxwell-Boltzmann, delta is here, t is here, solve it, and you are having the answer of the question 0.008, means 8 by 1000, means 8 atoms among the 1000 atoms will show the transition. Now at normal room temperature, 3 lines are visible, observable to us, mu equal to 0 and mu equal to 1. So for mu equal to 0 we are having mu equal to 1, 2, 3 which are observable, and for mu equal to 1 which are not observable to us, 2, 3 and 4 which is not observable to us. चलो आगे बढ़ते हैं. देखो यही था अपना mu equal to 0 पे 3 ऑब्जर्वेबल है, mu equal to 1 to 3, और mu equal to 1 पे mu equal to 2 to 4. Now fundamental transition we considered m equal to 0 which will be most intense. So mu equal to 0 से mu equal to plus 1 which is observation. For observation what will do? 0 minus mu minus 1. So what will you get? Just put in the value. What was the delta mu? Where it has gone? This omega e minus 1 minus chi e 1, mu plus 1 by 2. So put it mu equal to 0. So omega e 1 minus chi e by 2. Omega e 1 minus chi e by 2. Where it has gone? Yes. Omega e 1 minus chi e by 2, and then omega plus 1. So 1 minus omega e chi e by 2. And then for 1 plus 1 you will solve it. You are given what you are having for fundamental 0 to 1, 1 minus 2. Okay. And delta m equal to plus 1 is what will happen? For observation, I'll explain to you. For observation, initial minus final. Delta m equal to plus 1, mu plus 1 minus mu, mu plus, so delta m equal to, just reverse it, na, plus 1 to 0 plus 1, and here 2 minus 0 is delta equal to plus 2, and 3 minus 0 equal to 3. Getting my point? Final minus initial. So for this, for first, this is first overtone, this is second overtone, this is fundamental. So fundamental what is there? Mu 0 to mu plus 1, and for first overtone mu equal to 0, mu equal to 2, and third overtone, second overtone, sorry, mu equal to 0 to mu equal to 3. And how will you remember that? For fundamental 1, 2. For fundamental 1, 1, 2. Just remember it, okay? For fundamental 1, 2. For first overtone 2, 3. For second overtone 3, 4. And you are as good, comfortable. And chi is 0.01. So for good approximation, what will happen? Mu equal to 0 to mu equal to 1. Omega e bar. Delta e mu equal to 0 to mu equal to 2. So 2 omega e mu equal to 0 to mu equal to 3. We are having 3 omega Okay, just fundamental omega e, 2 omega in, 3 omega e, 2 omega in, 3 omega e. And if you know the exact what will, this is omega e, so 1 minus 2, 2 omega e, to 2 minus 1 minus 3, and 3 omega e, 1 minus 4, 2 3 3 4 1 2. Now we'll discuss about force constant of bond, k equal to y omega equal to 1 upon 2 pi dot k upon mu. होता है ना ओमेगा इक्वल टू नोट के बाई एम वाला, रख दो यहाँ से, ये सेम टू सेम है भाई, इसमें मल्टीप्लिकेशन किसका हो रहा है, इसका सी स्क्वायर का सेंटीमीटर इनवर्स के लिए। तो देखो बहुत इंपॉर्टेंट है, हर्ट्ज को सेंटीमीटर इनवर्स में बदलना है तो 1/c, और सेंटीमीटर इनवर्स को हर्ट्ज में बदलना है तो सी से मल्टीप्लाई करो। हर्ट्ज को सेंटीमीटर बदलना है तो सी से डिवाइड, और सेंटीमीटर को हर्ट्ज से बदलना है तो क्या करो, गुणा करो, सी का मल्टीप्लिकेशन करो। नाउ वी डिस्कस अबाउट हॉट बेल्स विच आर सेंसिटिव टू टेम्परेचर mu equal to 1 to 2 and mu equal to 1 to 3. Just calculate population, relative population 0 to 1 and 0 to 1. For 300 Kelvin 0.01, for 600 Kelvin 0. Means we are, if we are increasing temperature 2 times, then probability increasing 1 to 9 times. And delta mu equal to plus 1, mu equal to 1 to 2, 2 minus 1, mu equal to 1 to 2. What is this? 1 to 2 fundamental, then first overtone, then second overtone, then third overtone, and this is omega e 1 minus 4e, which will be slightly lower than the fundamental frequency. So far so good. Now we'll discuss about bond Oppenheimer approximation.